Hello everyone, my name is Gary Wang, and this is my research project about the comparison between traditional cast and Wrought 316L stainless steel. So here is a brief overview between the difference between traditional cast and Wrought 316L stainless steel. So for traditional cast, it is primarily sand casting, and it has pretty precise investment casting, and it exhibits evenly distributed equiaxial grain structure. It produces parts with lower yield strengths and lower tensile strengths, and it has an overall higher ductility. For Wrought 316L, it is mainly produced through hot forming operations. It has an overall larger grain structure and a lower yield strength, and it offers superior corrosion resistance. Here is the common features of the traditional cast and Wrought 316L. So they all consist of an iron base with 16 to 80% chromium, 10 to 14% nickel, and 2 to 3% molybdenum. They also offer highly stable face-center cubic crystalline structure with a much larger and equiaxial grain structures. The grain size are usually from 10 to 20 micrometers, with a fully annealed Wrought sample averages up to 47 micrometers. They also offer superior ductility, like for example offering greater dislocation and movement and plastic deformation, with the breaking range from 35% to over 70%. They also offer the lowest yield strength, and typically between 170 to 450 millipascals. Moreover, they also have an interesting fact of their strength and ductility parameters decreases as the test temperature rises. They are highly standardized in aerospace, medical, nuclear, and chemical industries. They also offer excellent corrosion and oxidation resistance and a high resistance to radiation damage. So here is the manufacturing specifics for cast 316L. The heat treatment for cast 316L is called solution annealing, which is referred to as a process of recrystallization heat treatment. The process typically involves heating the material to about 1040 Celsius and holding it for at least 1 hour. So after the soaking period, it is then rapidly cooled to freeze to produce the desired structure. Here is the microstructure changes of the cast 316L as it goes through production. This traditional casting method involves slower cooling rates that can lead to undesirable microstructural features. Solution annealing is used to dissolve metastable high-temperature phases such as the ferrite, which can form during the slow cooling of a large cast ingot. If it is left untreated, these phases can undergo degradation at higher temperatures via the phase decomposition and segregation. This treatment helps in healing chromium depletion at grain boundaries and reducing the sensitization, which significantly improves the material's anti-corrosive properties. The structure results in an evenly distributed and coarse equiaxial grain structure, with a grain size typically around 10 to 20 micrometers. Here is a microstructure of the cast 316L. Here is a diagram of labeling the grain boundaries, and then the diagram is at a scale of 5 micrometers. So as mentioned before, the grain size is between 10 to 20 micrometers, and they are prone to form a coarse dendritic microstructure. The larger grains and straightforward boundaries allow for greater dislocation movement and higher ductility, and it also provides a very high phase stability across an exceptionally wide temperature range. Here is the resulting properties of the cast 316L. This is a diagram of a piece of equipment hardware manufactured using the cast 316L stainless steel. So the treated material facilitates greater dislocation movement and plastic deformation as seen in the higher ductility. And then the austenite structure remains highly stable across an exceptionally wide temperature range, which is the root cause of 316L's consistent performance in harsh environments. While solution annealing reduces yield strength compared to AM additive manufacturing versions, it still provides high material consistency and predictable performance under stress, which makes it a very good material for high applications where stress is greatly required. So now let's move on to Wrought 316L stainless steel. The Wrought 316L is very similar to Cast 316L, where it is also utilized a solution annealing for the manufacturing process. For example, it's typically tested and used in a fully solution anneal condition, and then it also sits at 1040 Celsius for at least 1 hour. This treatment is often applied following industrial hot rolling operations such as hot rolling, press forging, and extrusion. Here is a diagram of the Wrought 316L solution annealing during the solution annealing process. So the Wrought 316L microstructure changes are as follows. They are usually large coaxial grains with an average interset length of approximately 47 micrometers. And one difference between Wrought and Cast is that in Wrought, the solution annealed after solution annealing, it may exhibit many straight grain or twin boundaries. At the subgrain level, this Wrought condition is notably clean and lacks the nanoscale oxide inclusions, often found in parts printed from powder feedstocks. As for the microstructure, it has larger grain sizes, approximately 47 micrometers, and is more evenly distributed, may contain straight grains or two boundary, allowing for greater dislocation movement. It lacks the nanoscale oxide inclusion. It has no compositional variation or elemental disintegration. It is often used as fully solution anneal condition, and it is a more coarse microstructure, which can experience high local stress concentrations at grain boundaries during deformation. Here is a diagram of the Wrought 316L microstructure. We can see the grain boundaries, grains in a 50 micrometer scale. So the resulting properties of Wrought 316L is as follows. It is a highly stable austenite face-centered crystalline structure, and then it produces the lowest yield strength, approximately 261.1 millipascals, among common 316L variants. But it offers a total elongation reaching approximately 72.8%. The uniform structure is achieved through solution annealing, helps the healing chromium depletion at boundaries, which improves anti-corrosive properties and provides excellent resistance to radial damage danger in reactor service, making it an ideal material for environments where highly radioactive processes is occurring. So now, here is the tensile properties of the two materials. Conventional 316L is characterized by larger equiaxial grains that facilitate greater dislocation, which leads to superior ductility, but it has a lower initial strength. Like, for example, let's see. The yield strength of Wrought 316L in a fully annealed condition has the lowest strength overall, with the tensile strengths are usually around 261 megapascals. The industry minimum for conventional form are often set at 170 millipascals. However, it has the ultimate tensile strength, which is between 485 millipascal to 580 millipascals. Some investment casting variants often range to 482 to 586 millipascals, which is equivalent to 70,000 to 85,000 psis. For ductility, the elongation at break is consistently higher, which reaches to 35 to 72.8, and the standard 72.8%, and the standard minimum requirement are often set at 40%. For elastic modulus, the Young's modulus value of the conventionally manufactured 316L is approximately 193 gigapascals. So now, as for the tensile property, here is a diagram of the grain microstructure, and here is a diagram of the engineering strain over the stress over engineering strain diagram of the austenitic 316L, which is the type explored from the Cast and Wrought. Compared back to additive manufacturing techniques, so The yield strengths of Wrought and cast are usually lower, the ultimate tensile strength is moderate, but the ductility is higher, which is superior than additive manufacturing. The grain structure are coarse and equiaxial, and the design complexity is limited compared to additive manufacturing. Surface quality of Wrought and cast 316L are usually smoother and higher precision. The production scale of Wrought and cast 316L is better for mass production, while additive manufacturing is better for lower volume productions. The material efficiency is lower for Wrought and cast 316L. The main defect risk is that elemental segregation in large ingots for Wrought 316L. The common heat treatment is solution annealing at 1040 Celsius, as mentioned before. So the key takeaways is that additive manufacturing 616L is significantly stronger, and then additive manufacturing is more cost-effective for high complexity. Wrought and cast materials remain the industry standard for safety-critical applications such as nuclear or aerospace structures due to their predictable isotropic properties and long-term documentation. Here is the phase diagram at different temperatures. We can see the temperature, the graph showcasing the different phases that material experience before it reaches the 1040 Celsius scale. So here are the carbon limitations, and then there's brittleness, and then the faceability, which is mostly in flexible austin state, across the temperature range from 600 to over 1400 Celsius. And then there's also printing stability, which is helped to keep the state stable by stopping unstable phases, and then the better melting and flow, and also the heat treatment results. Here is the general applications of Wrought and cast 316L. They are pretty useful for oil and petroleum industries, chemical transportation, pulp and paper processing equipment, aerospace and aviation structure, boat fittings, orthopedic implants, surgical equipment, medical benches, nuclear reactor core and coolant system components, heat exchangers, food processing equipment, and large-scale brewery equipment. These applications make it pretty popular for wide applications and general applications. This is the end of my presentation. Thank you.